Yo, what's up? What's up? Welcome back. Today we're working on my operating system. It's an x86 operating system. It's written in Rust. Right now we are kind of working like in a virtual machine. So we have this like operating system. QEMU will boot it. It has like some features. We have like a web stack, a graphics stack. We have like a game that runs and a demo. We basically got like a little demo kernel running. So let's just like pop that open real quick. Which I think will be in this window is probably where I want to do this. So let's just do like a cargo run here. So what this guy will do is he's gonna run my operating system in release mode. He's gonna boot QEMU after I set up my environment correctly. And oops, 1 second. I need to correctly enable my like network card that's required for this to boot right. So just 1 second. So I disable the one for my other user and enable the one for this user. Okay, let's try it again. So we run the OS. See, we're booting QEMU. We have a little like brick breaker demo. And this is running like in parallel with some other stuff. So if I open up like netcat and try to talk to my OS at a fixed IP with a fixed port, I can say like, hello. And we see that like our OS is logging to the serial console, which gets piped into like the standard output of QEMU, and he's setting stuff back. So we're doing something. And what we're working on right now is we're kind of like doing this, we're working towards multi-core support. So right now, everything's running on one core, and the like way we get concurrency is through Rust's async await model. And what we're working towards is trying to support the same model, but over multiple threads. So what we're looking at right now is we kind of have like a demo function. We'll just draw like a little block for it down here maybe. Call it demo. And in here we have things like TCP, which handles like that like echo server. And we have like game. And like maybe within here we might have like some like draw, so like a sleep in here and some like draws, render. And in here we might have like, we might also have like Ethernet, etc. But what like the problem here is that this is like kind of like a tree of work. So what happens is we kind of like package up this like single thing, the demo, and we send this off into our like, we put it into our like executor, Qtor. And what happens is we do these things, and when there's like stuff to do, somebody will tell our executor, like someone being like a CPU interrupt triggered by like keyboard input or Ethernet driver or like Ethernet card input or like timer input. He goes like, hey, it's time to do some work, man. Get moving. And the demo goes like, oh shit, yeah, I gotta do something. And he goes like, hey, Ethernet driver, do you have something to do? And the Ethernet driver's like, no, I'm busy, like, I'm good. No, network's coming. He's like, TCP, do you have something to do? And he's like, well, obviously not, because the Ethernet card hasn't given me any data. And then he goes, game, do you have something to do? And the game's like, maybe, let me check this guy. And he goes like, sleep, do you have something to do? And the sleep's like, yeah, I finished. Yeah, the clock said we're good to go. And he's like, okay, then I'll do a render. And then he does this whole thing again. And basically, like, every time we do any individual piece of work, we have to poll all of our subsystems to see if they're ready to work, which is like fine. The polling each of these is supposed to be like really cheap, right? You're not supposed to do something that's expensive in here. But I mean, we've written everything from scratch, and we might do something expensive in there. And it's like better. It would be better if instead of like packaging it this way, what's the best way to do this? Maybe I'll take the eraser out. So instead of all this, it would be nice if we could kind of like cut these lines up and kind of like register these guys with the executor directly. And then what happens is then the executor can be like, hey, it's time for this guy to make progress. Hey, it's time for this guy to make progress. It's time for this guy to make progress. And he could like explicitly say which one is meant to be done now. And that gives like us a couple things. One is it gives us the ability to split up this work more in a more granular way, right? Like with the old mechanism, we had one tree of work, and so that means only one core could do anything. We can only have one person that pulls this. But if we have like everybody registered independently, then we can say like, oh, CPU 1's handling Ethernet, but CPU 2 should be handling the game, and CPU 3 should be handling this render. Right? We could like split up the work more granularly. And also lets us run like multiple executors at a time. So we can run 4 executors and they could like all pull from the same queue of work, and that's great. And it's also more efficient because now we don't have to pull every single thing every time anything happens. We only have to pull the stuff that's like relevant to us. So that's where we're moving towards. The current state here is, I think I have to have a window open yet? No. So the current state is that we have this like future executor, and this is like where the work is really done right now. And it's pretty simple, right? It's very straightforward. He does some like initialization shit. We don't need to talk about that too much right now. And all he does is just infinite loops, and he says, hey, I'm starting a loop, so I'll just write down that I've done a loop recently. He pulls the one chunk of work, and he says like, are you finished? And if you're finished, I'll break the loop and I'll return. Otherwise, I'll check if you reset my like state to say like, no, keep going, please keep going. And then if there's no work to do at this point, then I know that there's nothing to do until an interrupt triggers. So I just like turn off the CPU. And when an interrupt fires, like by like an Ethernet packet coming in or like the clock moving a tick or something, this will get triggered. This will get kicked out of the loop, I should say. And if that we get kicked out of the loop and it says that we should keep moving, then we'll like pull again. So that's a current implementation. And what we want to do is, one, we want to get away from this like static variable, right? Like this is used in a like if we have multiple executors at once, they should have their own state associated with them. And we've got pretty close to that last stream. So last stream, we used to have like a free function that would set this from any interrupt handler. We've kind of propagated like state to all of them now. And so now we can support, now we just have to like do the work of actually like moving this into its own thing. Then we want to support like queuing extra tasks independently, like we talked about. Then we want to make sure that the tasks that we queue are should be sendable to other threads so that multiple threads of work can pick up the same data. And then we'll certainly run into bugs. And so we're gonna look at like what those bugs look like and try to fix them as we go, probably. Yeah, so that's what we're gonna want to do today. Hold on, my light is off and it's making my frame rate really low because the exposure time is too long. Just give me 1 sec, I'll be back. All right, is that better? Yeah, we're not at like 4 FPS on the camera anymore. We're at like 20 FPS, which is not great, but not awful. We'll live. Okay, so let's just hop in and start working on removing this like global static, which should be easy to do now. So we're at 8:45. All right, so let's just nuke this guy. Okay, so what's going on here is this waker is how you tell Rust's features that you want to wake up. So let's pull up the docs there. Waker from the Rust docs. So here they have this like waker guy, and he basically sets himself up so that he can be used. You call like waker.wake, and that tells the executor to keep moving. So that's our implementation, just backed by this Boolean. And I realized while I was reading the docs today, I think I saw a trait that we can implement for this. Oh, but it's only in core. Never mind. Okay, so how we're doing this is the way we're supposed to do it. So the idea is, I don't really know why it's only in stood. Let's take a look at this. This is in, it's in the alloc crate. Oh, because it takes an arc stuff. Okay. So there is this like wake trait that makes the implementation easier. But what we have right now is kind of like a C style variadic or a C style. What do you call it? C style inheritance, I guess, where you take in like a data pointer to like a void pointer, and you can cast that to whatever you want in a free function to get the data you need. And probably they just did it that way because otherwise you need allocations, and they didn't want allocations in like the core future spec, so that's fine. But what we'll do here is when we implement this, our new version, we're going to try to make use of this fancier wake trait. So we'll use alloc, and this is task, I think. Wake, yeah. And here we're going to make our like waker, so we'll have struct kernel waker. And inside, he's just going to have like a boolean that says should. This is, sorry, bools on the right side. We'll call it, what should we call? Should bool. Same thing that our current one's called. And this will be a bool. Great. I think almost certainly this is going to have to be an atomic bool, but we'll deal with that as it comes up. And we're now going to implement the wake trait now for kernel waker. And here he has a wake that takes in an arc, which is a reference counted atomic pointer. So here we'll pull that in. We'll say we want to pull in atomic arc, which just means that like you have some data and everybody from multiple threads might be holding a reference to that data, and when the last guy drops in and says like I don't need this anymore, then it'll get deallocated. Great. This isn't atomic arc, this is sync arc. And QRST, S comes before T, so we put it this way. We misspelled kernel waker here. Cool. And all we have to do for wake now is we say self should pull equals true. And we see an immediate problem here where this is not writable, so we can just make this an atomic bool like this, which means that we need to use atomic bool, which we already have. Great. And here we can just say store true with, I don't really know what kind of ordering here I want. If I did ordering relaxed, I guess there's a chance that in this loop we might think that we should halt the CPU and we shouldn't. So let's make this ordering, I think it's a release, right? When we are finished writing this, we need to sync up with people who are trying to acquire it. And I think that's our implementation of the waker. Easy. Let's just nuke all this shit. And now we're going to make our waker. So we'll say let waker is equal to kernel waker. And I guess we just instantiate this should bool is an atomic bool. And should his initial state be true or false? Probably false. Right? He has no reason to pull initially, except for we should pull once for sure. So I guess his initial state should be true. Here we need to maybe convert that into a context. So how does that work? They just say context from waker. So here, where does this guy come from? So let's look at context. And he has from waker that makes a waker. And then what is this like wake trait? How do we get from this wake trait into a waker? Here, he just calls into. So probably I guess waker has like a from on wake trait. From arc W global where wake is waker. Yeah. Okay, so we just say here from waker dot into like this. And I guess here we actually need to make this an arc, because that's the API for this. Great. So that's, we now have our waker, we have our future context, and now we just have to do this like same shit. So here we store the that we're pulled. So anytime we have should pull here, we just say waker should pull. And I think that's it. Here we need to clone the waker because he's passed off into someone else. So here we clone him. We say let context waker is equal to this, I guess. Or here's what we'll do. We'll do a little trick here. So here we have a context who wants to use this waker, but he wants to consume him, but we want to use him below. So what we usually would want to do here is we would want to clone, make a copy of the waker, which in this case just increases the reference count on our shared reference. But like making a new name for him is kind of like ugly, right? Like I don't want to make like context waker and pass him in because like that's mental overhead for me. But what we can do is we can say what waker is equal to arc clone and waker. We can do this in this scope so it doesn't leak out. This like other waker stays there forever, but we don't have to worry. Like it just makes like the usage of this thing a little nicer, which is kind of fun. Because what happens is in these braces, then it just like returns the last thing here. Oh, but this doesn't work because the context actually assumes that he wants to like borrow the waker. That's annoying. Wait, so why doesn't this actually work? I don't think I should have to clone this. I guess, maybe I have to do this. I convert this into a waker instead of an arc wake. This is now a borrow here. And here I should also be able to borrow the waker. Oh, but I've lost the internal details. Oy, 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 oy. Okay, so I do have to say let context. There's a way to do this without having to clone the waker. And I want to do that for my own fun. So here we'll take in a reference to an atomic bool. Here he'll have a lifetime. And here we'll say let should poll is an atomic bool. New true, great. And then here we pass him in to the waker. And we do an into here like this. And now we can use this should poll directly. Very nice, very nice. And here we need to say let context is equal to this. You just store it. Very, very good. Except that this atomic bool has to be static. Fuck! Okay. Fine, fine, fine. We'll just clone it. Let context waker is arc, clone, and waker. We pass in the context waker here instead. And here we don't use a lifetime on this guy anymore. He does have to just live in here. That's fine. And here we go back to atomic bool. New true. Great, and now we need waker on all of these guys. All right, that was a little bit of a saga, but it looks like this should work now. We have no more global, and let's try doing like a quick little cargo run release and see if everything's still working correctly. So we have our game running. We can talk to our server. He's sending stuff back. Yeah, overall, looks like things are working. Okay, so let's remove this. Do a little cargo, we do a little lint script. He doesn't like some formatting, so I cargo format, cargo clippy for linting. Everyone's happy, and we will say that was a quick little, okay, test pass. So we'll just do a little quick commit that says remove global wake up signal from future executor. Executor. There we go. I don't think there's any really context that's needed for that. I guess maybe we'll say replaced added kernel waker that implements wake, replaced should poll with member waker. Great. All right. So that is a quick little implementation that seems to be working, and that's at 19, let's say 20 minutes. Okay. So the next thing that we want to do is we want to support like a queue of work. Instead of doing one feature, we want to be able to support many features. And so instead of this like execute future function, we're actually going to want like some sort of structure that can hold multiple futures at once and pull them as individuals. So probably what we want is like, well, we want struct executor, and inside him, what's he gonna have? Let's say that he's gonna have futures, and each future is gonna have an ID so that we can like associate him directly with a waker. Let's think about that. I think that's correct, but we'll see. So in here, he's going to have just a future, I guess. I guess now that we have these, like, we might have, how to say this? Before, we executed a single feature of type future, right? Great. But now we have multiple features that won't have the same type, but they will have the same, like, API, I guess. So we do have to convert these into dynamically allocated array, like not arrays, dynamically allocated features, so that we can runtime resolve what they are. So this is dyne future. We need to use the box thing because this is an allocation thing, and since we're in like a no standard environment, we have to actually import that manually because we have an allocator. So we say it's okay, we have boxes, great. He doesn't have hash maps, right? So that comes from, I think, use hash brown hash map, which is like the hash map implementation that the standard library uses. But again, we don't have the standard library, so we just pull it in manually. He needs an output type now, so output equals this. Great. I think that's fine. So now what do? We have an implementation for the executor. And on here, we're going to have like a function spawn. And he's going to inject a future into this executor. Great. So what's he going to do? He's going to take in a mutable reference to self, I guess. And his futures, let's think about this. He's going to insert a future. So in here, we're going to take in a future f. And so we're going to take this in as a future. And we're going to inject him into the executor. So we're probably going to have like IDs that haven't been used yet. So we'll say ID is a usize. Usize is probably not what we want to use here. We probably want to use U64. We want to like be specific about this probably. We're going to say let ID is self.id. We're going to increment self.id, right? Because we've just used it. And then we're going to say future self.futures.insert. What does he take in? He takes in a ID and a box new future. And maybe we just should pin these now, because to pull them, they have to be pinned. I think. I'm not entirely sure here. What does this as mute do? I thought this converts himself into a pinned thing. Okay, sure. So we can just actually just do box new and stick the future in there. This needs a lifetime bound. Okay, so why is that? Oh, because when I stick them in the box. Sure, we'll try just shoving the static on here. There might be a way to dodge the static lifetime if we were a little clever with lifetimes. But we might not have to, right? It might be that this is like a totally fine API for everything that we use right now. So we'll kind of just see how that goes. In fact, we can just test this by adding a static on here and seeing if we still compile. And we do. So the fact that we still compile here means that we're chilling. So that's good, as of right now at least. So once we've stuck our futures into the list of futures that we want to pull, we actually need to pull them. So we'll take, maybe for now, we'll take ourself and we'll consume ourselves, right? For now. And the idea here is that once we've like put all of the work into our executor that we want to do, we just run it now. And so here, what are we going to do? We're just going to do what we did previously in this execute future. All of this just moves into this run function, I think. But the only difference is we need to create a waker per future, actually. So here, actually, we have futures, and we're also gonna have wakers. Maybe we should store these together. So struct, we'll call it like a task, maybe that's a bad word for it, but I think that's the nomenclature that they use in the Rust standard library. And we'll say that the future is of type box dyn future output is equal to this, nothing essentially. And he's also gonna have a waker, which is a kernel waker. And here we then need to make a waker for each of these guys. So we'll just say this. We'll just make our waker here. And here we will say that this is now tasks, not futures, which is a task. We create an ID, we get a waker, we get a future. And we say let task is equal to task. Use future is box new fut. Great. And the waker is a kernel waker. We just do this. Oh, we already have this. Sorry. So the waker is waker. And this waker needs to be behind a shared reference. Great. And now we can just insert the task. Boom. So now that we have our tasks, what we need to do in our run function is we need to see which tasks are like ready to go. And so how do we do that? We could just like walk the list of tasks. That's the like first naive implementation. But what we really wanted was when we wake up a task, we actually want that to queue itself in a way that it's like ready to go. So maybe what we should do is we have this like lock free queue, and we could use that as like a list of task IDs that are ready to run. And then we could just like iterate over those task IDs and pull those specific futures. In which case this like kernel waker is maybe no longer the right abstraction. It might make more sense for our waker to contain his ID, so U64, as well as the like a writer to our lock free queue. So we'll say we'll just call it TX. This could maybe even be a locked queue. I'd have to think about that. I think that a lock-free queue is just easier to reason about right now, even if it is like, I know that there are cases where they're like less performant or more performant. I don't really care. I just want something that like fucking works. So we'll use, oopsies, what the fuck did I just do? Use create util lock-free queue, and here we have self and sender and receiver. And so what we're going to do is when we wake, we're going to have a sender. Sender, I've capitalized a little too much up here, so let's do sender. This is a sender of type U64. That seems reasonable. Now when we wake, we're going to say tx.push or self tx push ID. Right? So say, hey, I specifically, me, my ID. I'm going to wake up now. Then in here, we don't need to store our wakers here. We can just say our task is a future. We don't make our waker anymore. I think. Let me think about this. Somewhere we need to associate the ID. I guess we'll leave the wakers in there for now. I need to think about this. Our waker needs an ID, so we'll say waker ID is ID. Great. And we'll say waker channel, or we'll say txrx is equal to what? Channel lock free queue channel. This is coming together. Okay. So what's going to happen? Our lock free queue is going to have a channel associated with them, and he's going to have that on construction. And each time we construct a new future on here, we're going to pull another writer for our global reader. So we'll say that our to run futures is going to be a reader, or is that what I called it? Receiver of U64 task IDs. Here we're going to say that our tx is equal to run sender. I think that maybe I should have like an API to pull an extra receiver off this, but I think instead I just have my sender can be marked as clone. And here I can like store a sender as well. So Q to run is going to be a sender of U64, right? And here what's going to happen is every time I create a new waker, I'm going to make a tx is self.q to run clone. Great. Because the way our lock-free queue is implemented right now is like a multiple producer, single consumer. So our writer side supports multiple shared references, but the reader side has to be a single mutable reference. So here, every time we spawn a task, we create an extra sender. Great. They all kind of like have like the same back storage. So it's just like an atomic reference count to that storage. Great. Okay, so now this starts to make a little more sense, right? So now here, our executor, first of all, he doesn't have an ID. I don't know what the fuck this is in here for. Oh, this is the next ID. Never mind, that's great. And so what he does is he says for ID, or I guess he loops, right? And what does he do here? When does he finish? What's his end condition? I don't know yet. We'll figure it out. But for each iteration of this, he's going to say, is there any work to do? So he's going to say, let task ID is equal to self to run pop. And maybe we're going to do a match here. And if we get a value, we propagate the value. Otherwise, there's no fucking work to do. And we need to wait for there to be work to do, which means that we need to do this. Just turn off the fucking CPU. Great. And continue. So on the next iteration of the loop, we'll check if there's any work to do again. If there's no work to do, we halt again. Great. We need to add a semicolon here. Okay. So at this point, we have guaranteed work. And so we say let future is the self tasks get task ID. So here we're going to do a little match to say, well, there might not be a task ID, right? If we, for some reason, removed it. It should be guaranteed, but maybe there's a bit of mistake in here. So we'll just say get mute. get the task ID. And I think we have to throw an ampersand in here. And if we get one, great. And if we don't get one, what are we going to do? We're inevitably going to continue, because like we can't continue with this thing, and we'll say failed to get task ID. I'm not sure if this error macro handles this properly, so let's just try putting in like some garbage here and see if it gets mad. It does, so task ID will be printed. Great. And then we try to pull the future. So I think we just say if f as mute dot pull context. We don't have a context right now, so we have to create the context for this future, which means that we need to pull the waker for that future. Aha! Okay, so we'll say let context is equal to this. So we create a waker, we create a context from a waker, but this waker is going to be, oops, this shouldn't be f, this should be task. And for the tasks, we have the context waker. Great. So we now, I think, ooh, arguments of this function are correct. Oh, I see. Context waker is an arc clone task waker dot into, and then here we pass in the context waker. That's a little disappointing, but it is what it is. Something about this isn't right, but we'll get there. We'll figure that out in a second. And then here we have the task dot future as mute pull. Okay, so there's a bunch of stuff here that it doesn't like. So we'll figure that out now. And here I'm just gonna say delete everything in here, and we'll say this is unimplemented. We'll come back to this. I just want to start seeing some compiler errors. Okay. So unsafe cell box maybe on init U64 cannot be shared between threads safely. That's odd. Oh, because sync is not implemented for the storage. Oh, okay. So let's look at this. So this waker is going to be sent around, which has a sender, which has arc storage. So this can't be sent around unless storage is sync. So I think this should be sync. Let's look at this. Yeah, there's no reason that this isn't sync. So let's impl unsafe impl send for sender t. And I think we have like unconditional sync and send implementations for this. I think is sane. Let's think about that for a second. Oh, did I already implement this somewhere? I did. Okay, let's go back down then. Here we have sync for sender, sync for receiver, and can I implement send for sender as well? Yep, that solves that one. And I'm almost positive that that's safe. I don't see any reason why it wouldn't be. Okay, and the other thing is this poll, he doesn't like that because he's not pinned. But I don't know why this used to be okay, but whatever. We'll just say that we have a pin box here, which requires us to import pin, so pin, which is basically just telling the it's like some like type bullshit to get the compiler to know that like this thing won't fucking move in memory. And here we just say box pin, I think. All right. So everyone's happy. And now I think all we have to do is in our execute future thing, we just create a new executor, which we can't do yet without a function new, which returns an executor. And keys just an executor with ID 0. Tasks is default, like an empty map. And we'll say let q2 run and 2 run is equal to lock free q channel new. Oh no, just channel. And then we can just say q2 run and 2 run here. Great. So here we need to say how large the queue is. So let's just let's say something like I don't know, what, 1024? Like, that's so many cute tasks that we'll never hit that, but maybe we'll, I don't know. Now we have probably some people when we push, we probably want to panic if that fails. So in our implementation of wake, we say match this, or I guess we can just expect failed to wake task. I think that it's reasonable for this to be like a full-on panic. Like we'll say that our assumption is that we have enough room, right? And if we don't have enough room, then we have to bump it up or surface faster or something. And I think that this is like a fair panic. I think that's fair. Okay, so here we make an executor. We spawn our only future, and then we run. Here we need the output. We can just do this. We just discard the output, and that converts it into the right thing. Card check. And let's see what happens if we run. I'm betting that something's gonna break. I bet right. I wonder if there's any way to like bisect why nothing's happening. Our logger's not running. Our brick breaker game isn't running. Keyboard input isn't running. So I guess maybe it would be interesting here to start like printing out what we get here. So let's maybe like, it would be cool if we could like print the state of the queue maybe. So let's say, what do we get out of here? This guy doesn't have a debug implementation, but I think that if we just derive debug here, we'll probably get what we know. We're not going to get like anything interesting there. Maybe what we do instead is we'll, in our waker implementation, here, somewhere, where's our waker implementation? Hello? Am I brain dead? Here we go. We'll say waking self.id. And here on the reader side, we'll check if we got any IDs. So print line running, or loop. And here we'll print the task ID. Got task ID, task ID. Here we'll say taking a nap, because there's no work to do. And here we'll say got task for task ID. And here, oh, this is a bug. Here we break. So I bet you this is it. But we'll see. So here he's looping, taking a nap. At no point is he supposed to do anything. So we'll disable these logs for now because they're flooding us. And let's see if he ever wakes up and does something. So here, that's interesting. Okay, so nobody at any point in time is trying to run the waker. Oh, and it's because we don't run the future once. So what we have to do is when we spawn, we have to queue up this future to run one time at least. So we'll say self.queue2run.push ID. That way, we have like one chance to get the right answer, and if we don't get it, then we're probably sorry. If we don't get anything, then we'll queue ourselves on the waker, etc., etc. Like our future will run, etc., as expected. And here we'll also just say failed to queue task for on executor or something. I don't know. It doesn't really matter. There we go. Okay, so we got something. He's doing some stuff. But he did crash, which is kind of annoying. Or freeze or something. It could be that like too many prints are causing this to slow down to the point where something's wrong. It could also be that there's just like something that's not correctly propagating its state. So let's maybe we leave these logs in. I'm fine with that actually. And we'll look at what happened. So somewhere he said waking 0, and then we never tried to run 0. So it'd be interesting to see why that is. Did I try to break it all? Let's see this. No? I'm just maybe out of curiosity, like just to see, I'm gonna disable these print lines. So we have seen in the past that we do crash if we print line too much too fast. So let's just try taking these out and seeing if that changes anything. And that does. Okay, so there's a bug to keep in mind for sure, that just printing too much crashes ROS, and I don't know why, but otherwise, this is working okay. Surprisingly. We resolved a MAC address. What happens if I try to like talk to this guy with netcat? That's all working? Oh! Failed to wake task. That's interesting. Okay. So we hit our first bug. So that means that there's just too many things queued to the point where we're not servicing this fast enough. Which could explain the crash earlier, actually, where the print lines were like making things take too long. I wonder if we can like maybe log the queue size as we go through here. So we'll say queue size is this, and we'll look at self.toRun.size, which doesn't exist right now, but we'll just make that function real quick. So this guy is a queue of, and in here he has a storage, and we'll just say pub function size takes in self and returns a usize. And what's he going to do? He's going to take in, he's going to look at self.storage, and our queue has a head and a tail and a reserved. So let's say that our head, I think we increment as we grow. So we'll say if self.storage.tail is equal to n, or self.storage. I think there's like a size in here somewhere. Elements dot len. We return max size. Otherwise, this shouldn't really happen. And I guess we have to load with ordering acquire. Cool. No method named len on this guy, because this is to be like a get, probably. Sure, unsafe, so we wrap this unsafe, great. We'll say len is equal to this, we'll just pull this little bit out. And here we'll return len. Okay, then we have else if the let head is equal to this. We want to pull these guys out now, and since they're atomics, then it's kind of a pain in the ass, so we'll just load with ordering acquire, and tail will do the same. And then I think if its tail is greater than head, then we do tail minus head. Else tail, I think it's greater than equal to. I can't remember. It is equal to when they are sorry. So I have a head and a tail, and I don't know if tail is supposed to be one passed or the same. So somewhere we'll have a if head equals tail, return none. So head equals tail is empty. So tail minus head, if this is greater than or equal to, if it's equal to, it return 0, great. Otherwise, we do head minus tail and like len minus head minus tail. Is that right? So if tail is, if head is 1 ahead of tail, we should be at like 1 minus, like len minus 1. And if it's 2 back, then it should be what, len minus 2. Yeah, that's right. And I think this should give us the how many elements are in the queue. So now if we go back to our future implementation, we have this like print line queue size. And this, if we're crashing because we can't push, we should start seeing this grow over time. Which means that we're like not servicing our futures well enough. Which we are seeing. And I bet, actually, now that I think about it, what's probably happening here is we're probably polling the same fucking future over and over and over and over again. Right? Because if we have a waker and his implementation is to push an element into this like receiver queue or this queue, say during a run, we push an element like 10 times. What's going to happen is we have to run that feature 10 times to clear it. And really what we want is like, we want like a set of things to run on the next tick. So let's think about that. I wonder if a spin lock in here is reasonable. Let me think this through. So we have many futures. They're all being run by the executor. When they call wake, can they acquire a lock reasonably? I think so, because the lock will only be acquired for the duration of wake. Then on run, I just need to make sure that the lock isn't held when I pull the futures. I think that's fair. I think that'll work. So let's look at the futures implementation. And now we're just going to ditch this like TXRX shit. And we're going to have like an arc spin lock. Sorry, not this one. Here, we're going to have like an let's think. To run is going to be an arc spin lock hash set Q64. Is this the right amount of brackets? No. So we're going to say self to run lock. Is lock not right? Insert self.id. Oh, it's hash set doesn't exist and spin lock doesn't exist. Right. So we need to pull those in. So in our utility module, we should have I think it's like this util. We have a spin lock. Man, I'm so glad I didn't delete that when I wrote it last time, because it's definitely coming in handy. And then from hash brown, we need hash set as well here. Great. Great. In here, now we lock insert the ID. Fantastic. And here, instead of sending in a TX here, we'll just say we'll clone R2 run. So R2 run now is over here, arc spin lock hash set U64. Great, and now our to run is just hash spin lock new hash set new, and actually we need an arc new here as well. Bing bang boom. And here this queue to run no longer exists. Fuck this lock free queue shit. Here we pass in to run is equal to self.to run clone. So we need like an arc clone of this guy. Boom. And we self.to run lock.insert ID. Boom. Boom. There's no longer a pop here. So is there like a hash set pull off and delete? Like I want like a pop. Pop, 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 pop. Take. Removes and returns the value in the set. I don't want that. I just want like, give me one. I don't really care. Just give me one. Drain is maybe the closest. Clears the set, returning all the elements in an iterator. But I kind of would like to be able to do this like in a loop. Drain might be the closest thing to what I want. Extract if, retain, clear with hasher, blah, 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 difference, intersection, get. Yeah, I really thought there'd be like a pop on here. But fuck it. All right. So we'll say for task ID in self.toRun drain lock.drain. Is that going to give me, does the drain takes myself by mutable reference? So probably what I actually want to do here is I want to pull out the items and temporarily and collect them in a vector. The reason for that is that I need to make sure that I release the lock. So we'll say toRun is equal to self.toRun lock drain collect. Right, so we're just gonna say put these in a vec, please. And I'm putting these in curly braces because I just want to be fucking sure that that lock goes away. I'm sure these probably aren't needed, but it's making me a little more comfortable. We need to import the vector type. Great. And now I just say for task ID in task into run, which will consume them as it moves. Then here I do all of this stuff inside that loop. And here I need to handle future finish because we're not supposed to pull it after it's done. And then here I just run the halt if there's nothing to do. I guess probably I only halt if there's nothing to do. So here I should actually halt up here if to run length is empty. Is actually the no name for what I'm looking for. Okay. Does this seem reasonable? No method size. We don't need this anymore. But I guess we can just look at the length of this. Nah, fuck it. And let's see if this runs. I think that that's good, but we'll see. So we got our logs. The OS is running. Yeah. Do we have netcat test hello. Yeah, okay. So it looks like that's actually working shockingly well. Oh, we did crash though. Fully crash. But I guess it's like hung, and we don't really know if it's crashed or not. There's a good, okay, so I'm like almost certain that some places in the code are not propagating wakeups correctly. Like, for example, on mutex unlock, we almost certainly have to wake up the people who are waiting on mutexes, right? But I know that I'm not doing that. So I think that that's like a very likely place where this is not working. Let's think. Probably the best thing to do here is to run in debug mode so we can pop open the GDB and kind of see where we're getting stuck. It's hard to do GDB with async functions though, because if we're just stuck in the loop of our future loop, then it's hard to say. Let's think. Let's pop open the code again, and let's assert. We'll first say panic, future finished, and I don't know what to do. Let's see if this is happening, because let's get the bugs that I know are there out of the way first. So interestingly, we didn't hit that panic. And let's, you know what, fuck it. Let's pop open GDB. Do I have debug symbols on release? I do. So if I just say GDB equals 1 cargo run release, we now need to pop open a GDB instance. And I think I just do GDB. First of all, I'm going to make a GDB script that says target remote localhost 1234. And what else does it do? It's going to load file target release kernel. And then I'm going to hit continue. This just makes my life easier, so I can just run a GDB, I think it's -x. Yep, so that's doing what I want, and there we go, we crashed, so let's take a look at that. And let's see where we are stuck. It's in a spin lock. Oh, that's interesting. So it's within our interrupt handler. We're trying to wake something up. Ah, fuck. Okay, I forgot that the waker is used from within interrupt handlers, which makes this really fucking annoying. Okay, so using a spin lock around a hash set as my implementation of awake is fucked. Absolutely fucked. Because within an interrupt, if we acquire a lock, we're like almost guaranteed to deadlock. Because if we ever interrupt while the lock is held, we're just like, fuck it. We can't get it. And we'll like never get ourselves out of that state. So we have to go back to like the queue implementation. So we'll just smack undo a bunch because that'll probably get us to where we want to be. Fuck the spin lock, fuck the hash set. I think this is probably where we were. Maybe undo a little farther. Yeah, around here. So maybe what I want to do instead is we'll still have a queue of things that we wanted to do. But what we'll do is on each iteration of our loop, we'll collect them all into one set. So we'll say let to run is equal to a hash set here, which means that we need to include hash set. And this makes sure that we service the queue to the point where hopefully we don't grow past a reasonable point. This needs to be mutable. And then we just say to run.insert. So the idea is that like maybe during one iteration of the loop, we tried to interrupt ourselves like 1,000 times on the same interrupt number. And we're gonna like look and be like, oh, it's the same one again, same one. And we're just gonna like turn that into one instance of toRun in this set. And then we're gonna say if toRun.len is empty, we have no work to do, so we just halt the CPU, take a little nap, which is this. And then we iterate over to the tasks that we've run. So for task ID into run, we do this shit. Great. We don't have to run on GDB anymore because we do not expect to be stuck. Oops, we have a waking log in here, which is going to, we know, crash the OS, I think. I think we know that. I think we proved that earlier. Well, proved to some extent. We noticed that. We observed that removing the print lines makes it less likely to happen. Okay, so this is still running. And if I netcat test hi, smiley face, surprised face, angry face. Yeah, looks like this is working to some extent. Which means that as far as we can tell, these like individual task-based wake up is working okay. Now, we are kind of still in the state where every single wake up will trigger the same task to wake up. right? Because there will never be a task ID that isn't 0 right now because we only spawn one future. So at the very least, that's working. So let's say that we refactored execute fut function into task spawner. Now we need to actually support task spawning. So maybe maybe we can say this is supported, and let's say update kernel demo to spawn individual tasks instead of join. Right. So what we want to do is we want to take our we now support theoretically running multiple futures kind of like in parallel. Yeah, that's not really correct. How do I say this? We can have many top level features that the executor is aware of. And so now what we want to do is we want to put those onto the executor as individual tasks and see if they still run correctly. Because right now we're still queuing only one tree of work. So let's make a little checkpoint here. Maybe let's do some linting as well. Card format, card clippy. So we have some unused imports here where we're not using atomic bool in future. Cargo format. I think I just fucked something out there. Yep, and cargo clippy, and we added this size function on the lock-free queue that we're not using anymore. But it is kind of like a nice debugging tool, and I don't want to re-implement this later, so I'll just say I'm going to allow unused on this guy. And maybe there's a argument to be made that I should just globally allow unused code. I don't think I really want to delete things that are useful, but maybe it's useful for like to be told that they're unused. I don't know. We'll just mark this one as allow unused for now. So let's run the linter, run our unit tests, because when we're working with the executor, there's a good chance the tests fail. Okay, so what's happening here? Borrowed data escapes outside of the function because, oh, so that static requirement that we made actually broke some of our unit tests. Why is that? Because it's using this like any failed thing. This is fixable, so I think I don't want to think about this too much, so we're just gonna make this a reference counted thing. I guess this is gonna have to be eventually an arc new atomic bool new false. We'll say here futures need to be static and send. And then here we'll say we need to clone this any failed guy, so we'll say let any failed is equal to arc clone any failed. There we go. Here we're gonna say any failed dot store true ordering release, and here we're gonna say if any failed dot load ordering acquire cargo check cargo test. We need to actually import this shit, so what do we have here? We need alloc arc sync arc, I think it's here. And we also need core sync atomic bool and ordering. There we go. Okay. Definitely the curly brace? I don't think so. Cargo test. This needs an async move, I guess. But that doesn't work because test functions aren't static, so this is actually just fucked. I actually can't do it this way. We have to make sure that our execute future thing doesn't require static. That's annoying. That is annoying. That's annoying. So can I remove the static requirement on spawn here? Maybe this needs to be tied to the lifetime of ourselves. Can I just do this? And I guess here our futures now need to have a lifetime associated with them. I guess. I don't know. I'm just kind of like bullshitting here. Which means that here we need a and lifetime a. Which means that down here we need a lifetime associated with the executor. Which means that here we don't need to specify a new lifetime. And here we probably don't need this. Cargo check. Okay, cargo test. There we go. Some lifetime bullshit. Right. And now our tests are not executing correctly. They're not ever finishing because we don't know how to handle the fact that we finished all our tasks. So I guess probably when a future finishes, we have to remove it from the executor. So we say self.tasks.remove task ID. And then here, when we are at the beginning of our thing, we say if we have no futures, return. That seems reasonable. And that runs successfully. Let's remove all of these print lines that we had in here. Yeah, I think we're chilling. So if I cargo format, cargo clippy, and run my linter, what do we see? Everything's good. Okay. So we'll say git add-u, and we'll say associate or add executor, add future executor. Add the ability to spawn tasks as individual chunks of work. This will allow for a work stealing executor in the future. A work stealing multi-threaded executor in the future. It also should theoretically improve performance as we only pull the features that we need. Very nice. Let's just double check there's not anything fucking stupid in here. So there's some like lock-free queue imports, some just general import stuff. Our kernel waker is now a queue sender that he like sends the ID of the queue he wants to wake up. Great. We crash if the queue runs out of space. That's fine. We have a task that has associated waker and future. We know that that's required because we need to pull the waker out when we run it to create a context. Our executor now has a sender and receiver because he needs to send one time when the future is queued. Great. Our spawn, does this look like pretty reasonable? So this is a lot of like diffs. So I'm just gonna I'm gonna come back and look at the executor stuff in isolation. So we can come back and say future, and let's look at this like executor stuff. So we create a channel of 1024. He's got some stuff that's reasonably default initialized. When he spawns a task, he like assigns it a new ID. He creates a waker, he creates a task, and he inserts those things and queues it to run. And when we run, we check if we have any tasks to run. If we don't, we break out. We collect all of our tasks from our queue into a hash set, and if there's nothing to do, we halt the CPU and wait for a new interrupt. Otherwise, we iterate over those tasks, polling once per thing. Yeah, there's nothing crazy in here. I think that's a fine commit. That is a fine commit. I'm happy with that. Was there anything that we added here that we didn't commit? Nope. All right. We are going to call that done at around 1:15:10. Great. And the next thing that we had on the list was update kernel demo to spawn individual tasks instead of join, and I still agree with that. Almost certainly there are going to be bugs there. I'm almost positive. We'll find out. So in our demo, what I actually probably want to do is I wonder if I can make this like a synchronous, like a non-async function that takes in the executor. Let's try that. And then the idea is that for each, like, we have like these like top level chunks of work, and instead of doing this join and await, I just want to spawn them all. I guess maybe we don't even have to take in an executor. So where do we do this? We have a demo feature here. And then what do we do? When we run our main function, we like create this demo feature and run it in parallel with the logger so that we get logs during the demo. So I guess like the first simple test would be let's get rid of this async main concept. We don't need this async main. We can instead put all of this in our normal main. And somewhere we have like a single await in here, and that's here. And all we have to do here is now we create our executor, which we need to now pull from our future implementation. So that means that there's like some like public sizing to do of this guy. So he's a public struct now. He has a public function new. He's a public function spawn. Public function run. We now need to pull this guy in from the futures stuff. So we're going to have future executor. And here's going to say executor spawn logger service and executor spawn demo future, and then we run the executor. And I think if we see, fuck, mute. Cannot borrow kernel as mutable because we have to define this as mutable here. Okay. So I believe that if we, if this works correctly, we see logs, and I think that if I comment this out, we should see no logs. Let's go! Okay, that's sick. Okay, so we now, we have like a real proof now that like the waker is correctly waking the logger service when it needs to log. There could be a bug where we're over waking, but at least there isn't a bug here where we're under waking yet, which is very nice. And we can probably also, maybe, I guess we could prove to ourselves that if we write things to the echo server, we're still seeing logs come out in the TCP subsystem. So I'm pretty stoked on that. That's pretty good. And so now what we want to do is we want to update our like kernel demo. So instead of doing like a future join, maybe we pass in the executor and he just queues up all the work that he actually wants done. So here, I guess, let's think about this. So either we're running our demo or a test. or we're running like unit tests. So I guess probably what we do is we do config test, and we'll spawn. I guess we don't actually have like a future to run in test mode. We just run our test main. And does our test main require any form of like sorry, I'm just thinking about what's going on here. So our test main is run from within the context of an executor, but I don't think it really has to be. I think our test main can be like a completely asynchronous function or a completely synchronous function. So here, we could say, instead of this busy waiter, we just while loop. So we'll say while kernel.monotonic_time.get is less than end. Then IO exit. Oh, this does need to be an async function though, just because the logger service needs to run. So then we can just actually, maybe what we do is we say, he does need the logger service to be running, and the logger service can only be done in parallel. And we do need this like sleep. That's annoying. Okay. So we'll leave this as is. And I guess we need a way to like queue up this test stuff. So I guess we just say, maybe we, I guess we make a function like test and wait. And he just does this, and he takes in the kernel probably by, looks like by reference. Right, we do this, and he just like hard quits the OS internally, so that's fine. This is an unsafe async function, I guess. But async needs to come first, so it's async unsafe function. Cannot find function test main, so we config test this guy. Test main is only available when we're in test mode. And here then we say config test. We spawn test and wait with the kernel. Now, this demo future is never queued. And we want config, I guess, we probably want to like change this behavior if we're in like test mode or not test mode. So I think we can have like config not test. And here we say executor spawn async, an async block. I think we can probably just do like kernel demo. So if I run cargo test now, nothing fucking happens. Oh, wait, no. Oh, it was just taking a lot of boot. Okay, config test, everything goes as planned. And if I run cargo run release, everything is good. Now, the problem is we've got all these warnings now because of this config not test. So probably what I actually want to do is in the config test mode, we do this. And then otherwise we just like behave as normal. And this should, I think, work okay. Yep, cargo test. But when I run cargo test now, it like thinks that this thing's been fucking moved. So I guess what I'll actually do is we'll just have a separate executor for test stuff. That's fine. Doesn't really matter. That's fine. It's not the end of the world. Not the end of the world. Okay. 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 Now, cargo test, no errors. Cargo run. We just have a unused thing. Otherwise, it seems to be working great. Okay, so now what we want to do is we actually want to say kernel.demo executor. Because we want the demo to just create things that it does. So we'll say let init demo is equal to an async block like this. He must take in a executor. And now just down here, we'll say executor dot spawn, and we'll just go through each of these. So actually, I think we can probably do like a quick little vim macro executor spawn this. Throw some executor spawns in here. And we also have to spawn the init demo. And we misspelled executor, executor. So I think this is, oh my gosh, that's impossible to look at. Executor. Executor. And then I guess we run it here. Which means, because we are using like local context, so we take them in full. And here we pass in the executor just like this. What's it mad at? Oh, because I put mute as part of the type. Fuck. And this mute actually goes in front of the variable name. Oh, fuck off. Okay, so we have the problem that the executor outlives. We have self is 1, executor has 2, and 1 must outlive 2. So the problem is that like it thinks that the kernel isn't outliving the executor. I guess maybe these pins aren't helping us. Okay. So let's just remove every single pin we can find here and see if that improves anything. Yeah, so the problem is that like it doesn't think that it can borrow the kernel, which is weird. Because this dies like right fucking here. So it's guaranteed to outlive the kernel. Oh, but I guess he's destructed after all of this stuff. Right. So the problem is that the executor has to get dropped before everything else. So can I like drop executor here? But he's already dropped. Okay, so what's he complaining about? He's saying that game dropped here while still borrowed. But that's just a fucking lie. It's not borrowed because the executor's been dropped and the stuff in the executor. Okay. So maybe it's my implementation of spawn. The lifetimes are actually not declared correctly. The lifetime of the future must be greater than myself. Well then, sorry, then the thing A. And A is the length of the future. So I wonder if I just put like this A here, does that actually fix anything? Wow. I think that fixed something, but made something else worse. Or just made something else worse. So borrow of executor occurs here. Cannot move out of, once it's borrowed, move out of executor occurs here. Oh, I see. So by doing that, it says that I'm tying the lifetime of the future to this borrow, which is wrong. I want it to be tied to the lifetime of the executor. We'll hit a little cargo check. So game is a temporary variable. Game is dropped while still borrowed at line 391. Here. Can we like, what if we do this? No, because it still thinks that the game is dropped before the executor, while the executor is borrowing it. Oi, 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 oi. Can I like put some lifetime constraints here? That's obviously wrong because the lifetime of the executor is too short. I feel like I'm missing something. I guess maybe the problem is that the lifetime of the futures of the executor are too long, given that because I'm like using it externally first. Like probably if I did this, like I didn't spawn this out here and attach the logger service to it, it would be fine. So maybe what I do here is my kernel demo creates his own executor. So I say executor new, make immutable, spawn all this shit. And that actually works great. And now here I can just spawn the logger service as well. Oh, that might be it. That might be it, baby. Oh, sick. Okay, and I knew this bug was gonna happen. I knew. Okay, so now we're at the point where our sleeps are not correctly flagging themselves. So we have like, oh, sick. Okay, so slowing down, brain. That's what's going on in my head. So we know now that we're now queuing up all of these futures independently from each other. And because of that, the propagation of wake-up events is now tied directly to each of these futures. And so now we see like things not happening because those propagations aren't happening, right? Like this game isn't making progress unless I hit a key on the keyboard because the sleeping, like it says like, I want to sleep for this amount of time. And when I'm ready, wake me the fuck up. And that's just not happening. I wonder like what else is broken here. So if I like try to send a TCP packet, that's also not getting propagated correctly. So I guess what we have to do is we have to start walking these one by one and fixing the lockups. Very cool. So we'll say that we've updated our kernel demo at this point, and this is at 134.53. And the next thing to do is start fixing bugs. So fix lockups due to things not waking up. And let's just like start pulling one at a time. So the obvious one to fix is this game loop. This one's like the easiest thing because we know that it's not updating. Well, I guess we know that it's updating on handle input. I wonder if we think that this sleep isn't happening. What happens in handle input? He just does like a pull. Yeah. So it has to be this sleep. And so the other day we went through and we like tried to improve the sleep service, and I actually realized after stream that we like made a very obvious mistake there. So the way this is supposed to work is we have CPU over here. He's got a line to a real-time clock. In this real-time clock, there's a rock, a little crystal. We like pump electricity into it. That looks like stink lines. We'll make them in yellow. That way, you know, they're lightning bolts, electricity. And he kind of like oscillates voltages based off of like a constant input voltage, I think, if I remember correctly. Every time he oscillates, the CPU gets like an interrupt. Right. So that's what's actually happening. On each interrupt, we run our interrupt handler, interrupt service routine. He has a reference to our waker. He also has a reference to a list. No, he doesn't have a reference to waker. He does, sorry. He has a list wakes. And the design here was going to be that the interrupt service... Oh, this is maybe wrong, actually. The design here was going to be that the interrupt service handler just calls this wake up. Let me double check. Yeah, no, this is right. He has a list of wakes. And the idea was that we have this like service function. And he has a mutex locked list of wakes. Mutex list. And the problem with a mutex locked list is that if you lock the mutex from within the interrupt service handler, then you're fucked. Because if the mutex is locked and then you try to lock it, you just instant deadlock. So the idea was that like we have like threads, thread 1, thread 2, thread 3. They're gonna like push sleeps to this guy. And he, when he's run, propagates those to the interrupt service handler, and the interrupt service handler will like wake up these guys when they need to. Now, what we needed to do here is we needed to propagate wake ups to these guys. So like not only do we need to tell this guy it's time to wake up, we need to tell this time it's time to wake up. And we kind of like fucked this up, and we actually only ever pointed the wake up at the service loop. Which means that we never wake up the task that's actually tried to sleep. Which is fine, to some extent. It just means that when we queue up a sleep time, we need to also queue up a waker. So what we have to do is find a way to propagate that info. So when we sleep, we create a sleep future. Sure. And he gets the monotonic time. He registers the wake up time. And now he just has to register a wake up time with the waker. So we'll just say register wake up time, and he has an end and a waker. Which means that he has a waker. And which means that this guy is going to be, we can kind of like do this trick to pull it out. So we say future pull function CX, and he just returns poll ready with the waker. Like this. Like this, yeah. And we await this guy. Await. So now we can inject the waker into this guy. And he can propagate the waker when he registers wake up time. Which means that this guy needs to be a U size and a waker. So he needs to push back a tick and a waker. But this guy's used for somewhere else. Fuck! Fuck. Undo. Instead, we do this here. We get say wakers equal to future poll function cx, and he returns poll ready cx.waker.clone, and we await that. So this one actually won't wake, so we'll immediately get our waker. Then we push back our tick and our waker. This guy does a U size and a waker. Now somewhere, this guy also needs a U size and a waker. This guy also needs a U size and a waker. Which means that this guy also needs a U size and a waker. So this actually can't be a U size and waker. This is to be a B tree map that goes from U size to waker, I guess, instead of a B tree set. Which means that this guy needs to be a B tree map instead of a set, probably. B tree map U size to waker. Great. Now this is B tree map new. And so when we propagate the sleeps over, we now insert the time and the waker. So here we have time waker, and we insert time waker. And here we have item waker, and I guess we don't actually need this, so we'll say this is nothing. And now we actually say for each item here, as we walk through this list, shit, hold on. So we try to get the first element here. So we say let nothing and the waker is equal to this, and we'll say waker wake by ref. And this is expected a time for sure. And now I gotta think about, like, when are we gonna run this service loop? This service loop should be run when somebody posted a wake up time, which is using this like mutex vectq. So really, we shouldn't have to wake this up ever, actually, because that should be handled by the mutex lock. But we also know that our mutex lock doesn't actually do anything. So for now, I'm just gonna like unconditionally wake this up for now. No, I'm not. I don't know. Well, we'll fucking leave it as is for now. Oops. So let's cargo run release and see if we get a game that runs correctly now. We do not. So I thought that this would work because I thought we would have propagated the wakers all up. So let's say we'll print here waking and just see if we at least get a log there, which we are not. So somewhere, I don't really understand. Here we get the waker. Here we post the wake up time to the waker. Let's see, maybe we don't ever get that log. Maybe there's a bug in here that I didn't expect. Pushed. So we did push some wake up times. In our interrupts handler, do we ever try to wake them up? No. That's interesting. So presumably it's because our service function is never queued. Our sleep service is never queued. So that's already bugged. Perfect. So what happens is these guys, they say, hey, service function, when there's like time, could you please like take this like multi-threaded data and like upload it to the interrupt handler, kind of? And he's just never running because nobody's ever queuing him. And what we need to do is, we need to make sure that when the mutexes are unlocked, that he's woken up. So let me just see where all of this is going. So this waker that we were using to coordinate with the interrupt, that's not required anymore. Instead, he's relying on this like mutex. So what we should do here is when we drop the mutex guard, we actually need to notify every waker that is waiting on this guy. Otherwise, they won't know that it's time that like somebody could get the mutex. So what should happen probably is when we like fail to lock the mutex, here we need to register waker with existing guard. Which is almost certainly going to be racy. Okay. I want to think about this a little harder. And I can feel myself kind of fading. I need to take a break, which means that I think what I'm going to do is I'm going to like pause this for now. I think that we've kind of like got some pretty good proof that our like future executor is actually working as we expect now. The executor itself has got an upgrade, right? It can spawn tasks independently, run them in parallel, and correctly identify which wake ups have or correspond to which futures. And now the problem is that our individual futures are like fucking broken. And so I think what I'm going to do is tomorrow I'm going to come back and try to like work through these one by one. Starting with the mutex one. And I just want to like maybe think a little bit about how I want to handle this type of thing before I come back to it. So, but yeah, in terms of like what we actually got done today, I think that the executor got a big upgrade. So I'm pretty happy with that. So yeah, if you enjoyed what you watched, I encourage you to come back. I appreciate the views. Yeah, and if you're watching on YouTube and you want to come swing by live, the Twitch is linked in the YouTube description. And if you're watching on Twitch and you missed stuff and you want to catch up, there's a YouTube link in the Twitch description. All of this code is open source and will be available here on the stream, my GitHub, and will be linked in the YouTube description if you're watching there as well. Yeah, thanks for watching. Catch you on the next one. Bye.